Okay, welcome everybody. Week 7 of network structures and cloud computing. Today we're going to talk about energy and power efficiency, and for practice we're going to do more networking stuff, which is going to enhance the the first socket practice that we did. So, data center energy efficiency. Um, as you probably learned through the textbook, one of the major factor in the business, the cloud computing business is cost, right? Because if cost was not driving this thing, we couldn't build a scalable solution because the needs for cloud computing was originated by the scale. People, ITs, organization were very happy with their small I don't want to say data centers, but micro data centers that they used to have, and in their computer room, and that was fine for those days. However, when we are growing up with when the scale and the demand for computing is growing, we need to have more capacity, and in order to store more capacity, you need to have more air condition, you need to have more water for cooling, you need to have more things that require an efficiency and energy efficiency optimization. So, and this is what we are going to discuss today. And essentially, it's when we talk about data center energy efficiency, we are looking at measurable unit, and then we are trying to assess what is the value of this unit of this ratio, and then trying to improve it. So the efficiency is the ratio between the computational work and the total energy used during the computational process. Okay, it's called power usage effectiveness, and it's a well-known term. It's called PUE. But essentially, in simple words, if you think about, you have a computer, and you're trying to operate it, and in order to operate it, it needs to be cooled, right? And it needs to be run in a way that you have an extra capacity if something goes wrong. For example, if the electricity goes down, you need to have some diesel or an in between until the diesel comes into action. You need to have the UPS batteries, and all these things have a price, and the PUE will indicate how efficient we are, what is the price that we are paying for getting the utility, the computational work. Okay? And basically this is the ratio, the total facility power divided by the IT equipment power. Okay? Having a facility that uses 100,000 kilowatt of total power, of which 85,000 kilowatt is used to power the IT equipment. So, and this is a pretty simple exercise. If I'm going to ask you what will be the PUE, it's basically the ratio between these two numbers. Okay, data center efficiency with respect to, if we wanted to look at how the energy overhead breaks down across the data center facility, let's first of all enumerate the things that we have. So the first one is the cooler, and then we have the chiller, the UPS, the batteries, the PDU, the power distribution unit. And I think you should know by now what PDU means. And then you have the lighting, the transformers, the switch gears, the cooling, the crack, and the rest of the IT equipment itself that is not related to the compute the compute it's the compute resource. So what and these are the key keys for optimal data center operations. And if you look at this pie chart, you can see what takes most of the efficiency. UPS is a very expensive things to have. It's a huge battery farms that supposed to give you up to 10 minutes from the power outage until the diesels are kicking in. And the cost for this UPS, for this battery farms, excuse me, as you see, it's 80%. High PUE values might indicate on high overhead. Sources of efficiency losses in data center. Stepping down high voltage to medium voltage to low voltage is something that can that has an overhead. So if you think about when your data center requires a 480 volt, okay? Now the 480 volt is transferred from the power utility center, and when the power utility center, in order to transfer and reduce the loss while it through the transformation, it needs to bring up the voltage into 110 kilovolt, and stepping down this high voltage to medium voltage as needed in the data center cost a 0.5% loss. And this is just an example. The UPS conversion loss is 10% because you have a DC and AC conversion. Delivering low voltage power 110 to the racks cable length that are greater than 100 meters is something also another 2% less. The crack delivering cool air over a long distance through fan power is 9%. So you get the idea of what are the area of improvements that are required to be applied in order to have an efficient data center operation. Improving the energy efficiency of data centers, you need to, one of the ideas is to raise the cold aisle temperature. One will say, if you remember, I don't know if you had the chance, but in the old days, in the old micro data center days, the excuse me, the computer room used to be freezing, and not anymore, because they learned that it's okay to have a little bit warmer temperature, and the server are still running effectively. Improved UPS again. One idea of improved UPS is to go away from the traditional UPS and have a small battery on the server level to handle a surge of lack of electricity. This is just one example. If you're more interested in this thing, you can take a look at the Open Compute server configuration, opencompute.org. It's pretty interesting things what they do there. It's basically the specification of Facebook hardware, Facebook and Microsoft hardware, and I think Google participates in this thing as well. Improve power distribution, as we said, we talked about the loss that we have when we bring up and down the voltage. Eliminate chillers, use water instead. Careful airflow handling. You can see lots of studies around these topics. Now, once that we have all these things and somebody's doing some change, we need to be able to measure it, because otherwise, how can we say that we were doing the right thing. And the canonical example is that when we are saying, okay, we were able to improve one of the things. How do we measure it? In a way that it is compared to the other measurement. Are we measuring it with some workload that was running? Because a computer that is overloaded will require more heat, will produce more heat and require more cooling, right? So we need to have a benchmark, okay? And this paper, Benchmarking Cloud Serving System with the YCSB, is actually a great example on how to do it. I recommend to everyone to go and read it. It's available through online. It's basically a classification of all kinds of workloads that fits to the cloud computing as we know it today. And based on this workload, they are measuring the PUE. So there is a kind of an end-to-end correlation between the PUE measurement and the actual value that was brought with this computing. And here are a few of the examples. You can say that, see, if you can look at this thing, they are measuring the throughput in operations per second, and you can see the 4 classification, and they have 4 different of workloads. The first one is Cassandra, HBase, Peanuts, MySQL. These are all an open source solutions, and they try to load it. Okay, they use some kind of they call it UCSB client, and they load the cloud serving store, and these are the examples of the results. Now, what we can see here, just as an example, you can see they measure the read latency. So, for example, you do select star from some MySQL, how long it took, okay, the specific instance to respond, okay? And as you can see that when you increase the throughput, increase the number of SQLs that are penetrating the instances, you can see, and it makes sense, that the read went up. And if we look at this thing, we can see that this one went up. The HBase, the more throughput we did, the HBase read latency went significantly high as opposed to the rest of the data set. And this is the example of the updates. And updates means that you are updating a table in the relational example for the MySQL. You can see that the more you go, the more you increase the throughput of the updates, you can see that they are sliding, that they are growing from, this is the MySQL, from 5 all the way up to 17, roughly. And you can see the trend. So I guess that what I'm trying to say is that when you have this capability, you can say, okay, I run this thing, and then I can measure the PUE, so I have an apple-to-apple comparison. I hope that that makes sense to you. And then there is another interesting article that I'm a little bit biased because I worked with Abhishek here, and they did pretty interesting things. They were trying to create to apply linearity between activity and power usage, and I guess that what they are trying to do is basically, if your server is not that busy, it's okay to put him in some sort of a sleep mode. Of course that it's not the sleep mode or the hibernate as you know it from your own desktop, but still it follows the same principle. It's they are applying all kinds of controls and protocol. They are establishing a protocol between the hardware and the software in order to effectively control the operations of the server and the rack. I recommend you also to go through this. It's pretty cool. Um, Data center power provisioning, optimized energy utilization associated with smaller electricity bit, $1 for 1 IT watt, assuming 0.07 kilowatt and PUE of 1. So I guess that what they're trying to do here is basically is to align the price with the PUE. And the motivation is pretty straightforward because you want to promote a more effective data centers. And the more IT watt per data center, the less overall operation cost. And it's, yeah. Now, but then when we say, okay, we want it to have to be more effective, so then we are cutting up on the cooling a little bit. So which means that the server will be a little bit warmer. We are risking our hardware to more failure, right? So then, so the risk for hardware failure increase, and then there is a risk for SLA violation. and we're going to and I'm going to show you in the next chapter, or I think it's later in these slides, that there are ways to mitigate it through software. So you can take the hardware, you can improve it, and then you can make all kinds of assumptions and take care of that in the software level. The simultaneous power usage characteristic of groups of thousands of machines over time, this is an interesting thing because you have lots of machines that are running, okay, and they are cool and all the things that we mentioned before, but then we wanted to manage it in a way that the rated maximum power of computing equipment is usually overly conservative, not useful. So we wanted to reduce and to take all kinds of assumptions that will improve it. And again, the YCSB, which is the benchmark, is supposed to help us to establish this baseline. So now, what we want to do is basically we have a data center that runs all kinds of stuff, but then when we are provisioning the resources to this server, what we are doing, we're basically getting requests from some user that say, hey, I want to have 1 VM, okay, and then another user say, okay, I want to have 3 VMs, and then another user say, I want to have X VMs. So basically, if we are trying to generalize the provisioning process in a data center operation, is basically an allocation of compute resources pair of tasks with deadline. Okay. Now, if you think about it, the chance that everybody will want the same thing because you have a big pool of cloud resources, you are not building this capacity based on whatever you need. So when you build a server, when you build a data center, you have more than 10,000 of servers, and you don't wait until you have 10,000 of requests for a specific demand. So I guess that what I'm trying to say is that there is some kind of a credit notion that the cloud provider has a capacity bank, a capacity pool, and it plays with this capacity as a bank and it is optimizing the provisioning process, and sometimes it is oversubscribing the facility power. So for example, if I have 10,000 of computers, I can sell 15,000 machines, because under the assumption that not everybody gonna ask for the 10,000 machines at the same time. And you probably don't like this assumption, but this is what all banks do, okay? Because they don't, because the chance that everybody will want their money in the same time is pretty low, and basically when it comes, it indicates on some really bad thing that happens to the economy. And I don't want to go in, I don't want to start an economy discussion here, but essentially I want you to get it to get familiar with the oversubscribing function, where basically you are hosting a number of systems that their cumulative peak power will exceed whatever you have. Okay, and this is the CDF, a function of the power of normalized power, and you can see that it's correlated, although that there is an 80% deviation. Okay, an 80% an oversubscription of power of 20%. So what we see here seems like a net, yeah, and this is what I said, like a bad idea, not really. Study showed the potential opportunity of oversubscribing. And please, if that doesn't make sense, please feel free to ask me a question, and we can talk about more details about the numbers. And that brings us to the practice. I'm gonna stop this session, so it's not gonna take me a lot of time to upload it to YouTube. I'm gonna create another session for this one. So stay tuned.